Let's find some integrals using those powers of secant and tangent that we just talked about. The first one is, okay, tangent cubed x over 2 dx. So this is a case where the tangent function is odd and there is no secant function. So what we've got to do is we've got to generate some secant functions so we can play nicely. So to do that, what I'm going to do is I'm going to rewrite this. Tangent x over 2 secant squared, tangent squared x over 2 dx. Now one thing I'm probably going to do here to make my life easier is I'm going to go ahead and use a simple u sub. I'm actually going to call it t sub. I'm going to say I'm going to let t equal x over 2. So dt is dx over 2. The reason why is I don't like x over 2's. I'd rather just be a t, right? That way you can focus on the form and not have to worry about juggling the argument there. So that's going to kick us out, like that's going to be like 2 dt equals dx. So I end up with 2 tangent t tangent squared t dt. Now from there, I know that tangent squared is secant squared x minus 1. So I get 2 tangent t secant squared t minus 1 dt. Okay, that's not too bad. So what that's going to allow me to do is it's going to split me into two integrals. 2 tangent t secant squared t dt minus 2 tangent t dt. Alright, so this tangent t minus 1 comes out here with another 2. So splitting that out is going to be very important because here what I can do is we can do two separate integrations. We can say, okay, for this one I can do a u sub. I can say u equals tangent of t du equals secant squared t dt. Now over here, this, instead of writing tangent of t, I could have just said minus sine of t over cosine t dt. The reason why you want to do that is for this one, now you can say u is cosine of t du equals negative sine of t dt. So what that allows you to do here is actually convert sines and cosines and go from there. So the negative gets absorbed. So negative sine t dt. So I end up with 2 integral 1 over u du. So let's not use u here because I think that's confusing. So it's 2 times 1 over v dv. And over here I just have 2 u du. That one's real clean, right? So this becomes 1/2 u squared plus 2 natural log of v. And of course you get a plus c. But the problem is that we need to convert all the way back. We need to say, okay, well, I definitely didn't start in u's and v's. I have to go back to t's, but I didn't even start in t's. T's are x's over 2. So that's actually cosine of x over 2 or tangent of x over 2. So that gives me 1/2 tangent squared x over 2 plus 2 natural log, that's actually the value of cosine x over 2 plus c. And that's really how you do it there. You just follow the process. But that splits it into. Now this one over here, this one's a little interesting because you can do this one a couple of different ways. The first way is if you look at it, you go, okay, well, I can actually do this by u substitution, like old school u substitution. I could say, okay, well, I just take u to be tangent, du secant squared times 3 dx. Right, that chain rule gets us as 3 dx. So I could really just rewrite that as 1/3. So then that gets absorbed. This becomes 1/3 u du. One sixth tangent squared 3x plus c. Now that is one way to do it. But another way you could do it here is by trying to use, it's still a u substitution, but it's a little more in line with what we've learned already, which is to say, okay, I'm going to rewrite that as now I have a secant and a secant tangent. So I can do my u here. I can say, all right, I want to let u be secant of 3x. So du is secant 3x tangent 3x times 3 dx. Right, that's a secant tangent, and then chain rule gets me my, you have to get that 3 dx. Or I can rewrite that as like that. So then when I pull that in, I now have 1/3 u du. So I have 1/3 u du, which again gets me 1/6 u squared plus c, which is 1/6 secant squared 3x plus c. Now, I want to point this out because why aren't these the same? I have a 1/6 and a 1/6, but I have a tangent squared and I have a secant squared. But tangent squared and secant squared are not the same function. So how in the world is this equal to that? Well, then you might say, okay, well, I'll use my trig identity. Alright, so I'll use my trig identity here. So I have the same thing, but now I have an extra 1/6. How can these possibly be the same thing? How are they both right? Well, this is a good example to talk about what an arbitrary constant is. Now remember that the whole idea between antiderivatives and derivatives is that the function that gets generated by one of these, like every function that actually gets generated by an antiderivative, they're all the same function except they differ by a vertical shift or an arbitrary constant. And what this is sort of a junk box term for some sort of height. So really this shouldn't be a c. This should sort of like be c2 and c1. They're really not the same arbitrary constant. And what you find is that there's a little bit of a relationship there between what those constants actually are. And that relationship is at 1/6. But the whole point of the arbitrary constant is this is sort of this junk box constant term. Like this isn't a constant and this is another constant. So put together they still just suck up into a single constant. So they really are the same because that constant is really only useful to us when we are solving things like initial value problems, differential equations, things like that. They become very, very important then. Other than that, you just sort of have, again, it just becomes this sort of junk box. You just lump all your constants into there. So for practical purposes, instead of writing that, you would just write this plus c. That's a standard convention on how to solve those types of problems.